Hi, welcome to Supervised Learning with scikit-learn. Here you get a chance to grow your machine learning skills with scikit-learn and discover how to use this popular Python library to train models using labeled data. In this course, you'll learn how to make powerful predictions, such as whether a customer will churn from your business, whether an individual has diabetes, and even how to classify the genre of a song. Using real-world datasets, you'll find out how to build predictive models, tune their parameters, and determine how well they will perform with unseen data. This course consists of 4 chapters, which are classification, regression, fine-tuning your model, and lastly, preprocessing and pipelines. In this video, we'll cover Chapter 4, where we'll learn how to impute missing values, convert categorical data to numeric values, scale data, evaluate multiple supervised learning models simultaneously, and build pipelines to streamline our workflow. To begin our final chapter of the course, first we will cover preprocessing our dataset for accurate results. Recall that scikit-learn requires numeric data, with no missing values. All the data that we have used so far has been in this format. However, with real-world data, this will rarely be the case, and instead we need to preprocess our data before we can build models. Say we have a dataset containing categorical features, such as color. As these are not numeric, scikit-learn will not accept them and we need to convert them into numeric features. We achieve this by splitting the feature into multiple binary features called dummy variables, one for each category. 0 means the observation was not that category, while 1 means it was. Say, we are working with a music dataset that has a genre feature with 10 values such as electronic, hip-hop, and rock. We create binary features for each genre. As each song has one genre, each row will have a 1 in one of the 10 columns and zeros in the rest. If a song is not any of the first 9 genres, then implicitly, it is a rock song. That means we only need 9 features, so we can delete the rock column. If we do not do this, we are duplicating information, which might be an issue for some models. To create dummy variables, we can use scikit-learn's one-hot encoder, or pandas get_dummies. We will use get_dummies. Links to web pages and datasets used in the upcoming slides are given in the description of this video. To get started, first download the latest Python from the official website you can see in this screenshot. Next, you need an integrated development environment, IDE. I would recommend using PyCharm Community Edition, which is a Python IDE, but you can also use any other tool of your choice which supports Python development. After downloading PyCharm, install it and create a new project with configurations you can see in this screenshot. We will be working with a music dataset in this chapter, for both classification and regression problems. Initially, we will build a regression model using all features in the dataset to predict song popularity. There is one categorical feature, genre, with 10 possible values. This box plot shows how popularity varies by genre. Let's encode this feature using dummy variables. We import pandas, read in the data frame, and call pd.get_dummies, passing the categorical column. As we only need to keep 9 out of our 10 binary features, we can set the drop_first argument to true. Printing the first 5 rows, we see pandas creates 9 new binary features. The first song is rap, and the second is blues, indicated by a 1 in the respective columns. To bring these binary features back into our original data frame, we can use pd.concat, passing a list containing the music data frame and our dummies data frame, and setting axis equal to 1. We can remove the original genre column using df.drop, passing the column, and setting axis equal to 1. Lastly, we can export the resulting pandas data frame to a CSV file. Opening this CSV file in Excel, we can see the corresponding dummy variables against each record. If the data frame only has one categorical feature, we can pass the entire data frame, thus skipping the step of combining variables. If we don't specify a column, the new data frame's binary columns will have the original feature name prefixed, so they will start with genre_, as shown here. Notice the original genre column is automatically dropped. Once we have dummy variables, we can fit models as before. Using the music_dummies data frame, the process for creating training and test sets remains unchanged. To perform cross-validation, we then create a k-fold object, instantiate a linear regression model, and call cross-val_score. We set scoring equal to neg_mean_squared_error, which returns the negative MSE. This is because scikit-learn's cross-validation metrics presume a higher score is better, so MSE is changed to negative to counteract this. We can calculate the training RMSE by taking the square root and converting to positive, achieved by calling numpy.square root and passing our scores with a minus sign in front. Now let's look at how to handle missing data. When there is no value for a feature in a particular row, we call it missing data. This can happen because there was no observation or the data might be corrupt. Whatever the reason, we need to deal with it. Previously we worked with a modified music dataset. Now let's inspect the data frame by replacing all negative values with none so that we have some NA values to test with. Now, to calculate the number of none values, we chain pandas.isNA with .sum and .sort_ values. We can see duration and loudness have missing values. A common approach to clean data is to remove missing observations. To do this, we use pandas.dropNA method, passing a list of columns with missing values to the subset argument. If there are missing values in our subset column, the entire row is removed. Rechecking the data frame, we see no missing values. Another option is to impute missing data. This means making an educated guess as to what the missing values could be. We can impute the mean of all non-missing entries for a given feature. We can also use other values like the median. For categorical values we commonly impute the most frequent value. Note we must split our data before imputing to avoid leaking test set information to our model, a concept known as data leakage. Here is a workflow for imputation to predict song popularity. We import simple imputer from scikit-learn.impute. As we will use different imputation methods for categorical and numeric features, we first split them, storing as categorical feature and numeric features, along with our target array. We create categorical training and test sets. We repeat this for the numeric features. By using the same value for the random_state argument, the target array's values remain unchanged. To impute missing categorical values we instantiate a simple imputer, setting strategy as most frequent. By default, simple imputer expects numpy.nan to represent missing values. Now we call .fit_transform to impute the training categorical feature's missing values. For the test categorical features, we call .transform. For our numeric data, we instantiate another imputer. By default, it fills values with the mean. We fit and transform the training features, and transform the test features. We then combine our training data using numpy.append, passing our two arrays, and set axis equal to 1. We repeat this for our test data. Due to their ability to transform our data, imputers are known as transformers. We can also impute using a pipeline, which is an object used to run a series of transformations and build a model in a single workflow. To do this, we import pipeline from scikit-learn.pipeline. Here we perform binary classification to predict whether a song is rock or another genre. We convert values in the genre column, which will be the target, to a 1 if rock, else 0, using numpy.where. We then create features and target array. To build a pipeline we construct a list of steps containing tuples with the step names specified as strings, and instantiate the transformer or model. We pass this list when instantiating a pipeline. We then split our data, and fit the pipeline to the training data, as with any other model. Finally, we compute accuracy. Note that, in a pipeline, each step but the last must be a transformer. Data imputation is one of several important preprocessing steps for machine learning. Now let's cover another, centering and scaling our data. Let's use df.describe to check out the ranges of some of our feature variables in the music dataset. We see that the ranges vary widely. Duration_ms ranges from 0 to 1.62 million, speechiness contains only decimal places, and loudness only has negative values. Many machine learning models use some form of distance to inform them, so if we have features on far larger scales, they can disproportionately influence our model. For example, KNN uses distance explicitly when making predictions. For this reason, we actually want features to be on a similar scale. To achieve this, we can normalize or standardize our data, often referred to as scaling and centering. There are several ways to scale our data. Given any column, we can subtract the mean and divide by the variance so that all features are centered around 0 and have a variance of 1. This is called standardization. We can also subtract the minimum and divide by the range of the data so the normalized dataset has minimum 0 and maximum 1. Or, we can center our data so that it ranges from -1 to 1 instead. In this video, we will perform standardization, but scikit-learn has functions available for other types of scaling. To scale our features, we import standard scaler from scikit-learn.preprocessing. We create our feature and target arrays. Before scaling, we split our data to avoid data leakage. We then instantiate a standard scalar object, and call its fit_transform method. passing our training features. Next, we use scalar.transform on the test features. Looking at the mean and standard deviation of the columns of both the original and scaled data verifies the change has taken place. We can also put a scalar in a pipeline. Here we build a pipeline object to scale our data and use a KNN model with 6 neighbors. We then split our data, fit the pipeline to our training set, and predict on our test set. Computing the accuracy yields a result of 0.805. Let's compare this to using unscaled data. Here we fit a KNN model to our unscaled training data and print the accuracy. It is only 0.515, so just by scaling our data we improved accuracy by over 50%. Let's also look at how we can use cross-validation with a pipeline. We first build our pipeline. We then specify our hyperparameter space by creating a dictionary. The keys are the pipeline step name followed by a double underscore, followed by the hyperparameter name. The corresponding value is a list or an array of the values to try for that particular hyperparameter. In this case, we are tuning in underscore neighbors in the KNN model. Next we split our data into training and test sets. We then perform a grid search over our parameters by instantiating the grid search CV object, passing our pipeline and setting the param underscore grid argument equal to parameters. We then fit it to our training data. Lastly, we make predictions using our test set, printing grid search CV's best underscore score underscore attribute. We see the score is very slightly better than our previous model's performance. Printing the best parameters, the optimal model has 12 neighbors. We've covered all parts of the supervised learning workflow, but how do we decide which model to use in the first place? This is a complex question, and the answer depends on our situation. However, there are some principles that can guide us when making this decision. The size of our dataset plays a role. Fewer features means a simpler model, and can reduce training time. Also, some models, such as artificial neural networks, require a lot of data to perform well. We may need an interpretable model, so we can explain to stakeholders how predictions were made. An example is linear regression, where we can calculate and interpret the model coefficients. Alternatively, flexibility might be important to get the most accurate predictions. Generally, flexible models make fewer assumptions about the data. For example, a KNN model does not assume a linear relationship between the features and the target. Notice that scikit-learn allows the same methods to be used for most models. This makes it easy to compare them. Regression models can be evaluated using the root mean squared error, or the R-squared value. Likewise, classification models can all be analyzed using accuracy, a confusion matrix and its associated metrics, or the ROCAUC. Therefore, one approach is to select several models and a metric, then evaluate their performance without any form of hyperparameter tuning. Recall that the performance of some models, such as KNN, linear regression, and logistic regression, are affected by scaling our data. Therefore, it is generally best to scale our data before evaluating models out of the box. We will evaluate 3 models for binary classification of song genre, KNN, logistic regression, and a new model called a decision tree classifier. We import our required modules, including decision tree classifier from sklearn.tree. The workings of decision trees are outside the scope of this course, but the steps for building this model are the same as for other models in scikit-learn. As usual, we create our feature and target arrays, then split our data. We then scale our features using the scalars.fit_transform method on the training set, and the .transform method on the test set. We create a dictionary with our model names as strings for the keys, and instantiate models as the dictionary's values. We also create an empty list to store the results. Now we loop through the models in our models dictionary, using its .values method. Inside the loop, we instantiate a k-fold object. Next we perform cross-validation, using the model being iterated, along with our scaled training features, and target training array. We set CV equal to our k-fold variable. By default, the scoring here will be accuracy. We then append the cross-validation results to our results list. Lastly, outside of the loop, we create a box plots of our results, and set the labels argument equal to a call of models.keys to retrieve each model's name. The output shows us the range of cross-validation accuracy scores. We can also see each model's median cross-validation score, represented by the orange line in each box. We can see logistic regression has the best median score. To evaluate on the test set, we loop through the names and values of the dictionary using the .items method. Inside the loop we fit the model, calculate accuracy, and print it. Logistic regression performs best for this problem if we are using accuracy as the metric. Well done on completing the course. I predicted that you would. To recap, You have learned the fundamentals of using supervised learning techniques to build predictive models for both regression and classification problems. You have learned the concepts of underfitting and overfitting, how to split data, and perform cross-validation. You also learned about data preprocessing techniques, selected which model to build, performed hyperparameter tuning, assessed model performance, and used pipelines. Congratulations again, and thank you for taking the course. I hope you enjoy using scikit-learn for your supervised learning problems from now on. Feel free to ask any questions in the comments section and we'll be pleased to answer those. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. See you in the next video.